Hi guys, welcome back to part 3 transition metals. In part 1 and also part 2, we have learned about the how to write down the electron configuration of transition elements, and in part 2, we have discussed about the trends of the transition metal in periodic table. So in this part 3, we will discuss or we will learn about the interesting properties about transition elements. So as you can see here, we have a few interesting properties of the transition metals, such as they are colored compound, they have magnetic behavior, they are actually have been using in medical applications, they have various biological activities, they have various oxidation state, coordination number, and also as well as geometry. So in this part, especially for the chemical properties, we will be discussing about the oxidation states, the metallic behavior, color and also magnetism, and last but not least, chemical behavior. So for the oxidation state, as you know, transition elements can be used all or most electron in the bonding. Okay, and they have various oxidation state. So as you can see from here, higher oxidation state, for example scandium, through the manganese equal to group number, they can easily combine with the oxygen and also fluorine. Okay, so here we have VO4 3-, and the oxidation number of the vanadium is positive 5. So here, you need to be able to calculate the oxidation state. How to calculate the oxidation state of the transition metal? So for example, we have VO4 3-. You need to be able to identify or to calculate the oxidation state of the vanadium. What is the oxidation state of the vanadium? So how to calculate this one? So you write down the V and then plus with the 4 oxygen, 4 times -2, because oxide is -2, and then equal to -3, because overall charge for VO4 is -3. So the vanadium is actually positive 5. So this is how you need to be able to determine the oxidation state. Other than that, for example, let's say the transition metals that have multiple oxidation state, we have iron, we have cobalt, and also nickel. Okay, with the few oxidation state. And then other than that, we have to exercise here in order to, you need to determine the oxidation state for the dichromate, the Cr, and then you need to be able to determine the oxidation state for the manganese. So let me show you one example. For example, here dichromate, Cr2 O7 2-. So you need to determine the oxidation state for the chromium. So you have 2 chromium, and then you have 7 oxygen. So 7 oxygen, 7 times -2, and then the overall oxidation state for the whole ion here is the -2. So 2 chromium, you will get positive 12. And then divide by 2 for each chromium here is actually positive 6. Right, so please find the oxidation state for this manganese. We will discuss about this part during our virtual class. And then, other than that, these transition metals, okay, have a few oxidation state. As you can see here, most stable, these are actually the most stable oxidation numbers are shown. For example, scandium, the most stable one is in +3. Okay, then we have chromium, stable one in +3, manganese in +2, and so on. Then, why these transition metals are coloured? So, what happened if a chemical is coloured? Is actually it must be absorb light. Okay, why colour? So, if a chemical is coloured, it must absorb light. Okay, it must absorb light. So, the colour is the transmitted portion that is not absorbed. So, in order to absorb light energy, the atom must have what we call an empty electronic orbital that is just a little higher in energy than the field orbitals. So, the d orbitals of transition elements generally meet this requirement. So, in order to have a colored compound, you need to have compound that can absorb light, okay? And second one, it must have empty electronic orbital, which is what we call the d orbital here. So here, this is the first one, and this is the second one. Okay, in order to have the colored compound, absorb light and d orbitals, empty d orbital. Other than that, this d element actually, this electron partially fill the sublevel. They actually can absorb visible wavelength light and move to higher d orbital. So it will give a striking color, except for the titanium and zinc, because they are actually colorless. Other than that, for the magnetism, this is what we have learned before this in molecular orbital theory, the magnetism. As you already know, we need to know two terms of magnetism. First one is the paramagnetic, where it is actually attracted to magnetic field. And how to determine this paramagnetic? It must have at least one electron or unpaired electron. And then second one is diamagnetic. It is actually unattracted to magnetic field and they are actually paired electron. So, as you can see, for example here, we have manganese 2+, where the electron configuration is Ar3d5. So, as you can see, when you draw the d orbital here, because the d orbital we have 5 orbitals, so the d5 you need to put electron singly in each orbital. So this is so this manganese 2+ is actually a paramagnetic because they have unpaired electron. Okay, for example, we have manganese 2+ with Ar3d5. Okay, miss 3 here. Please add on the 3 here, Ar3d5. Okay, then if you want to draw, we have 5 orbitals for the d orbital. Okay, so 1, 2, 3, 4, 5. You need to fill up all 5 electrons singly. 1, 2, 3, 4, 5. Then this one, this manganese 2+ is actually a paramagnetic compound. While what about the diamagnetic compound or diamagnetic ions here, for example zinc? So the electron configuration for zinc is actually Ar3d10. 3d10. Okay, as you know, we have 5 orbital for the d orbital here. Right, then you need to fill up singly one by one. And then you need to pair up 1, 2, 3, 4, and also 5. So zinc is actually a diamagnetic compound. In this case is zinc 2 plus. And then other than that, we have these are the examples of the color of the representative compounds of the period 4 transition metals. Titanium here, as you can see, is in white color. Vanadium sulfate dihydrate, and then we have potassium ferric cyanide, sodium chromate, and so on. So here we have copper, and then we have cobalt in pink color, and then nickel in green color. And then last but not least is the chemical behavior. Okay, last but not least for this part is the chemical behavior. What happened to the chemical behavior? The reactivity increased down the group from top to bottom. For example, chromium, okay, where the here, other than that, ionization energy increases down the group because, okay, for example, we have stronger reducing agent here. Chromium is larger than molybdenum and also tungsten. And then period 5 and 6, they have similar chemical behavior. Okay guys, so that's all for today. We have finished up 3 parts. Part 1, electron configuration. Part 2, the trends of transition metals in periodic table. And last but not least, the physical properties and also the chemical properties of transition metals. So we will continue our discussion in our virtual class and also WhatsApp. So I think that's all for today. Hope to see you guys again. Bye!